First, let me start with a couple of notes. That presentation will be fast, like really fast and a bit dense. So sorry about that. I just needed to pack a lot of stuff into 40-minute talk. So let's start with a note that a transcript of that talk is available on Dropbox tech blog. So it is an extended version with examples of how to profile your stuff, how to monitor for any issues, and how to verify that your tunings has actually worked. So if you like the talk, go check out the blog post. It should be somewhere at the top of Hacker News by now. So seriously, go read it. It has a ton of stuff. You might like it. So about me, very quickly. I was SVI at Yandex Storage, so we were mostly doing high throughput stuff there. I was SRE at Yandex Search. We were mostly doing low latency stuff there. And now I'm a traffic SRE at Dropbox, and we are doing both of these things at the same time. So about Dropbox Edge. So Dropbox Edge is NGINX-based proxy tier designed to handle low latency stuff, for example, website views, along with high throughput data transfers. For example, block uploads and like file uploads and file downloads are high throughput data types. And they're handling both of them on the same hardware at the same time. Couple of disclaimers before we start. So this is not a Linux performance analysis talk. If you need to know more about eBPF, perf, or BCC, you probably need to read Brendan's Greg blog for that. This is also not a TLS best practices compilation. I'll be mentioning TLS a lot, but all the tunings you apply will have huge security implications. So read a bulletproof SSL and TLS, or like consult with your security team. Like, do not compromise security for speed. Also, this is not a browser performance talk either. So your tunings that will be described here will be mostly aimed at server-side performance, not client-side performance. So read High Performance Browser and Networking by Ilya Grigorik. And finally, last but not the least, the main part of the talk is do not cargo cult optimizations, like use scientific method, apply stuff, verify each and every tunable by yourself. So we'll start with the lowest layers and like work our way up to the software. So on the lowest layers, we have hardware. When you pick in your CPU, try looking for AVX2 capable CPUs. You need at least Haswell. Ideally, you will need Broadwell or Skylake, or recently Epic. Epic has good performance also. For low latencies, you want to avoid NUMA. You want to probably disable HT. If you still have multi-node servers, try utilizing only a single node. That will help with latencies on the lowest levels. For high throughput, look for more cores. More cores are generally better. And maybe NUMA is not that important here, maybe. For NICs, 25G, 40G NICs is probably the best ones here. So they do not cost that much, like you should go for them. And also look for active mailing lists and community surrounds drivers. Like when you will be troubleshooting driver issues, like that will be very important. For hard drives, try using flash-based drives if you are buffering data or caching data. That will be very, very important. Okay, so let's move to the kernel stuff. Here, right in between of kernel and your hardware, there will be firmware and drivers. Rule of thumb here, upgrade frequently but slowly. Don't go bleeding edge, like stay a couple of releases behind. Don't jump major versions as far, like when they just released. Like don't do dumb stuff, but like update frequently. And also try to decouple your driver updates from your kernel upgrades. That will be one thing less to troubleshoot, one thing less to think about when you upgrade your kernel. That way, you can, for example, pack your drivers as DKMS or pre-built drivers for all your kernel versions. Just decoupling really helps troubleshooting. On the CPU side, your main tool will be probably turbostat. Turbostat allows you to look into MSR registers of the processor and see what frequencies it is actually running at. And if you are not satisfied with current, like the time CPU spends in idle states, you can set your governor to performance. If you're still not satisfied, you can set energy perf policy to performance. If you are still having CPU spending a lot of time in idle or you are dropping packets for some reason, try setting a CPU DMI latency to 0. But that's for very high, like very low latency use cases. For memory side, it's very hard to make generic memory management advices, but generically you should set THP to M advice. Otherwise you may accidentally get like 10x slowdown when you are going for like 10-20% increase of speed. And unless you went with utilizing a single NUMA node, you probably want to set zone reclaim to 0. Speaking about NUMA, that's a huge subject, like really huge. But it all comes down to that recent hardware, like all modern servers are actually multiple servers packed together in a single silicon. So you can ignore that, disable it in BIOS, and just get mediocre performance across the board. You can deny it, for example, specifically by single node servers. That's probably the best case if you can afford that. Or you can embrace NUMA and try to treat each and every NUMA node as a separate server with separate PCI Express devices, with separate CPU, separate memory. So let's move to network cards. Here you will be mostly using ETH tool, and you'll be using it for looking stats of your hardware and looking at and tuning your hardware at the same time. So let's start with ring buffer sizes. So rule of thumb here, it's the more it's generally better. There are lots of caveats to that. Like lots of them, but more like bigger ring buffers will protect you against some minor stalls or packet burst, but do not increase them too much, because like it will also increase cache pressure, and on older kernels it will incur buffer bloat. Sorry. So on the next thing to tune is interrupt affinity. For low latency, you should really pin, like limit number of queues you have to a single NUMA node, then select a NUMA node where your network card is actually terminated, like physically, and then pin all these queues to CPUs, like one-to-one. For high throughput stuff, generally it's okay to just spread interrupts across all your CPUs. There are, again, some caveats around that. You may need to tune stuff a bit, like bring up interrupts processing on one NUMA node and like your application on other NUMA nodes, but just verify it by yourself. You have that flexibility. And interrupt coalescing. Like for low latency, generally you should disable adaptive coalescing, and you should lower microseconds and frames. But just don't set them too low. If you set them too low, you will get interrupt throttling, and it will actually increase your latencies. For high throughput, you either can depend on hardware to do the right thing and like enable interrupt coalescing, adaptive interrupt coalescing, or just increase microseconds and frames to some particularly large value, especially if you have huge ring buffers. That will also help. Then on hardware offloads inside the NIC, The recent NICs are very smart, and I can probably give a separate talk about just hardware offloads, but there are still a couple of rules of thumb you can apply. Do not use LRO, use GRO. LRO will break stuff miserably, especially on the router side. Be careful with TSO. TSO can corrupt packets, it may stall your network card. Stuff may break. TSO is very complicated, it is in hardware, so it highly dependent on like firmware version drivers, and just GSO on the other side is okay. And again, on the older versions of kernels, it will lead to buffer bloat, either TSO or GSO, so be careful there also. On packet steering side, it generally on modern hardware, it's okay to rely on the network card to do the right thing. If you have old hardware, for example, some 10G cards can only RSS to the first like 16 queues. So if you have 64 CPUs, like they won't be able to steer packets across all of them. On the software side, you can have RPS. So if your hardware cannot do that efficiently, you can still do that in software. And for example, use RPS and spread packets across more CPUs. Or if your hardware cannot RSS the traffic type you are using, for example, IP in IP or GRE tunneling, then again, RPS can help there. XPS is generally okay to enable, it's just free performance, enable it. So now we are up the stack, up to the network stack. So this is a great picture stolen from Making Linux TCP Fast paper from the basically people who brought you BBR and like Linux network stack performance improvements for the last like 4 years. So it's a great paper, go read it. It's fun to read, a very good summary of a huge work. We will start again with the lowest levels and go up. So fair queuing and pacing. Fair queuing is responsible for sharing bandwidth fairly across multiple flows, as name implies. And pacing spreads packets within the flow with regard to sending rate that is set by congestion control protocol. So when you combine both of them together, you can use fair queuing and pacing. This is a requirement for BBR, but you can still use it with Cubic, for example, on any other congestion control protocol. So it greatly decreases retransmit rates. So we've observed like minus 15, 20, 25%. So which improves performance. So just enable it. Again, free performance. For congestion control, there have been lots of work done in the area. Some is done by Google, some by Facebook, some by universities, and and people are usually using Cubic by default. So we've been looking at BBR for quite a long time, and this is data from our Tokyo POP. So we had a 6-hour, some months ago, we had a 6-hour BBR experiment. And you can see that download speed download speed went up for pretty much all percentiles. So the clients we considered bandwidth limited actually were basically TCP limited in some sense, or congestion control limited. But enough of that. Let's talk about ACK processing and loss detection. Again, that's a very frequent theme in my talk, that use newer kernels. Like in newer kernels, you will get new heuristics turned on by default, and all heuristics will be slowly retired. And you don't need to do anything. You upgrade your kernel, you get these for free. So upgrade your kernel. It doesn't mean again that you need to stay bleeding edge. Like just stay couple the same guidelines as for firmware and driver supply. Like upgrade slowly but frequently. You cannot actually do any network optimization talk without mentioning Sysctl. So here is some do and don'ts. So let's start with stuff you shouldn't do. don't enable time wait recycle. Like, it was already broken for NAT users. It will be even more broken in newer kernels, and it will be removed. So don't use it. Don't use don't disable timestamps unless you know what you're doing. Like, it has very unobvious implications. For example, for sync cookies, or like there are many. So unless you know what you're doing, you've read the code, don't disable them. Stuff you should do on the other hand is you should probably disable slow start. There is no you should probably disable slow start after idle. There is no reason to keep it on. You should also enable TCP MTU probing, just because internet is full of ICMP black holes, and like you should enable it. And read and write memory, you should bump it up. Just don't do that too much. Just match it to BDP, otherwise you may get weird in kernel locking. Oh, that went fast. So now we are at library levels. So we will discuss the commonly used libraries in the web servers. If all previous tunings were basically applicable to pretty much any high-load network server, these are more web-specific. So for web-specific stuff, if you notice, and again, only if you notice that you have lots of time and more than it should, like lots of time NGINX or any other web server spends in compression or deflate symbols. So if you run perf-top, you see deflate there, then maybe it is time to switch to a more optimized zlib version. For example, Intel and Cloudflare both have zlib forks. If you see stuff around malloc, so you either see memory fragmentation or you use lots of that malloc takes more time than it should, then you can switch your malloc implementation to GE malloc or TC malloc. That also has a great benefit of decoupling your application from operating system. It has its own drawbacks, of course, but generally you don't want to troubleshoot new malloc behavior when you like switch operating systems, for example. So or upgrade your operating system. So decoupling is a good thing. You will also get introspection profile and stats and stuff. If you see PCRE symbols in perf-top, then maybe it is time to enable JIT. I would say it is a bit questionable. Like if you need to, if you have lots of regular expressions in your configs, maybe you need to just rewrite it. But again, you can enable JIT and see how it behaves in your particular workload. For TLS is a huge subject. But we will try to quickly cover it. So first, you start by choosing your TLS library. Right now, you can use OpenSSL, you can use LibreSSL, and you can use BoringSSL. There are other forks, of course, but the general idea is that the library you choose will greatly affect both your security and performance, so be careful about that. And let's talk about symmetric encryption. So if you're transferring huge files, then you will probably see OpenSSL symbols on perf-top. Here, I can advise you to enable ChaCha. First, it will diversify your ciphers use, so you will not be AES only, which is good. Second, if your library supports that, you can enable equal preference cipher groups and let client decide which ciphers to use. For example, your server will still dictate the order of preference, but within the same group, client can decide. And for example, low speed mobile devices will pick ChaCha instead of AES because they don't have hardware support for AES. For asymmetric encryption, you should use ECDSA certs along with your RSA certs, just because they are 10 times faster on the server side. Again, on the server side. And another advice is don't use uncommon crypto parameters. let me elaborate on that. First of all, uncommon crypto is not really the best one from security standpoint, so you should do that only if you know what you're doing. Second, great example is 4K RSA keys, which are 10 times slower than 2K RSA keys. Don't use them unless you really need them, unless you want to be 10 times slower on the server side. Again, the rule of thumb here is that the most optimized crypto is the most common one. The crypto that is mostly used will be most optimized. Finally, we up to the NGINX level. So here we will talk about NGINX specific stuff. Let's start with compression. Here you need to decide what to compress first. So that starts with MIME types and gzip types. You can probably just auto-generate them from MIMEDB and just have all the types defined so your NGINX knows about all registered MIME types. And then you need to decide when to compress stuff. I had a blog post on Dropbox tech blog again about deploying broadly for static content at Dropbox. So the main idea, if your data is static, you can pre-compress it beforehand and get the maximum possible compression ratios. And it will be for free because it's an offline operation. It's part of your static build step. So when to compress is also a question. Try to pre-compress all the static. How to compress is also a question. Like, you can use gzip. NGINX also has third-party broadly module. You can use them both, for example. You also need to decide on compression levels. For example, for dynamic stuff, you need to optimize for full round trip time. Therefore, maximum compression. So round trip time means encryption, transfer, and decryption, and which means maximum compression levels are not probably the right thing for dynamic content. Buffering. So there are lots and lots of buffering along the way, like from your application through NGINX to user, starting from socket buffers to the library buffers like gzip or TLS. But the main idea is here, here we'll only discuss in NGINX internal buffers, not like library ones or socket ones. So buffering inside NGINX has its pros. For example, it has backend protection, which means if client sends you byte by byte, then NGINX won't hold the backend thread. It will get the full request, send it to the backend. On the response side, it's the same. If your client may be malicious, fetching 1 byte at a time from you, NGINX will buffer the response from your backend and free up that backend thread, and which can do useful work. So buffering has its pros. For example, backend protection. It also can retry requests. On request side, when you have full requests, you can actually retry it against multiple backends in case one request fails. Buffering also has its cons. For example, it will increase latency. It will also increase memory and I/O usage. So here you need to decide statically at config generation time what you want to buffer and what not. It's not always possible. You cannot decide where you want buffering and how much buffering, and where you want to buffer in memory only, where you want to buffer on disk. So you can always leave it up to an application to decide. So you can do that with XXL buffering header. So on response, your application might actually say whether it wants response to be buffered or not. Again, TLS. Oh, we talk a lot about that stuff. So on the NGINX side, you can save CPU cycles both on your client side and on your server side by using session resumption. NGINX supports session resumption through session IDs. It is widely supported on the client side also, but it requires server-side state, so each session will consume some amount of memory, and it is local to a box. Therefore, you will either need sticky load balancer or distributed cache for these sessions on your server side, and it's only slightly affecting PFS, so perfect forward secrecy, so it's good. On the other side, you can use session resumption with tickets. So tickets is mostly supported on the browser land. On the client, it depends on your TLS library. On the other side, it has no server-side state, so like it's basically free. But it highly depends on your key rotation infrastructure and security of that infrastructure, because of that, like it greatly limits PFS. It limits it to a duration of a single ticket key. Which means if attacker can get hold of that key, he can retrospectively decrypt all the traffic he collected. So again, there are lots of security implications to any tunable or on TLS layer that you do. So be careful about that. Like, don't compromise your users' privacy for performance. And speaking about privacy, OCSP stapling. You should really just do that. It may shake some RTTs. It can also improve your availability, but mostly it will protect your users' privacy. So just do that. NGINX also supports that. TLS record sizes. So the main idea is that your TLS library will break down data in chunks. And until you receive the full chunk, you cannot decrypt it. Therefore, during the config generation time, you need to decide what endpoints, or actually that cannot be enabled on per location basis. So you need to decide what servers are low latency and what servers are high throughput. If you cannot decide that on the during the config generation phase, you just need to use, like, for example, Cloudflare has dynamic TLS record patch, which you can apply, and it will just auto-tune. It will gradually increase your record sizes as request streams. Of course, you may say, why don't you just set it to like 1K? Because like if you set it too low, it will incur a lot of overhead on the network layer and on the CPUs. So don't set it too low. A really huge topic is like NGINX. So event loop stalls. NGINX has great architecture. It's asynchronous, event-based. It's parallelized by having multiple share-nothing processes, almost share-nothing. But when it comes to blocking operations, it can actually increase your tail latencies a lot. So the rule of thumb, do not block inside NGINX event loop. For example, great source of blocking is I/O. So if you are not, especially if you are not using like flash drives, if you are using spinning drives, enable I/O thread pool and like I/O write. So that way especially if you're using buffering or caching, like that will, I really have no reason to not enabling it. That way all your read and write operations will be basically asynchronous to event loop. You can also reduce blocking on log emission. So if you notice that your NGINX blocks on log writes a lot, you can enable buffering and gzip in access log directive. You can that won't fully eliminate blocking though. To fully eliminate it, you need to log to syslog in the first place. So that way your log emission will be fully integrated inside NGINX event loop and it won't block. And file close, like opening files can also be a blocking operation, so enable open file cache, especially if you're serving a ton of static or you are caching data. It went faster than I thought it would. Again, that was a lot. I've skipped the most crucial parts here to actually make it fit into presentation format and make it fit into 40 minutes. I've made a lot of compromises and I've skipped the most crucial parts, is how you actually verify whether you need to apply tuning and how do you verify that it worked, and all these tricks with perf, eBPF and stuff. So if you want to know more about that, go check out like tech blog. It has way more data and a ton of references, like references to source code, reference to research papers, references to other blog posts about similar stuff. So, wrapping up. Through that talk, we've mostly went through single box optimizations. Like, some of them improved efficiency and scalability and removed like artificial choke points that your web server may have. Other ones balanced like latency and throughput and sometimes improved both of them. But it is still a single box optimization that affects single, basically, server. In our experience, most performance comes from global optimizations. So, for example, good examples are load balancing, internal and external, within your network and around the edge, and inbound and outbound traffic engineering. So these are problems that are on the edge of knowledge right now. Even huge companies like Google or Facebook are just starting to tinker with this, especially outbound traffic engineering. If you like look at recent Sysctl, you will see that like both like Facebook and Google just released papers on that. So this is a very hot subject. It's full of PID controllers. It's full of like feedback loops. It's full of oscillations, and like if you are up to these problems or maybe anything else, we after all also do lots of storage. So if you're up for the challenge, yes, we are hiring SWEs, SREs, and managers. So feel free to apply. And finally, Q&A. I'm not sure how much time I have, but let's see how it goes. Also, I'll be here like today and tomorrow, and this is my Twitter, so you're free to ask that on any questions on Twitter.
Do the AIO settings affect reads, position writes?
Excuse me?
Do the AIO settings affect reads in addition to writes?
Yeah, by default it only affects reads, and if you do IO write, then it also affects writes. Like for example, temp file writes during the buffer and stuff. I think they are offloaded through AIO. So.
Yeah. You guys moved the ecosystem knowledge for the question on Sysctl?
So quick assist sounds nice, but there are a couple of caveats to that. It implies that your software needs to know how to talk asynchronously to the basically to your offload engine. Answering your question, no, we haven't tried. Presentation graphs from it look awesome, especially around 2K RSA. But again, it all depends on your. In case of SSL offload, handshake offload, it depends on OpenSSL library having support for asynchronous operations. They've added it in like OpenSSL 1.1, but like nobody is actually using it for now. Also, it requires hacks to NGINX. Intel did a good job at that, so they've released patches to NGINX to support like asynchronous OpenSSL APIs, but I'm not sure anyone is using them in production.
Yeah, we could test using efficacy for error size, before we use error size 2048. So each improvement in performance is projected. And when we migrate to ESI, we lost that.
Yeah.
We didn't see that.
Yeah, like stuff. The only use case for quick assist I see right now is basically RSA2K. Because ECDSA is very fast on the modern CPU. So stuff that I was talking about, like AVX and BMI and ADX capable CPUs, like Broadwell or like Epic, they are really good at elliptic curve stuff. And on the bulk data transfer side of things, AES-NI is very fast. You can do a gigabyte per second per core almost. So you don't need hardware offload there. You will hit other bottlenecks first. And on the compression side, like optimized version of zlib libraries that can use AVX instructions are also very fast. So. Anything else? I was told once that if I make that pause embarrassingly long, someone would actually ask something. Anyway, that's all. Thank you, guys. Go.